Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, this is a supplemental video for the homework for Chapter 7, which is building an analysis of covariance model. So I'm going to scroll on down to, we're looking at Chapter 7, but not the notes for this chapter. I'm just going to continue scrolling down to this homework assignment for ANCOVA 2. So this video is going to look at a data set similar to the one that we're looking at in class. The one we're looking at in class is Albuquerque home prices that I scraped off of the web last week. And instead we'll look at a different data set that will show you the main components of the assignment without giving away too many spoilers. I know you'd hate for the assignment to be spoiled. So, this is just my R Studio window, and I'm going to walk through the basics of the assignment using this other data set. So let me scroll down to this data, and I'll bring it up in my browser. This data set is about crash test dummies. So there's automobiles that they put, dummies, fake humans, into the car, and then they drive them into a wall at 35 miles an hour. And there's different sensors in the dummies to measure how much force the head has impact for, and the legs. And in particular, when we look at this data set, it's a little bit hard to see here, but we've got the make and model of the car. We have a car ID, okay, the car ID ain't near. But here's the real things. Head IC is how much damage there was to the head. I think IC is something about injury, something, I don't know, we'll look it up. Chest is sort of how much damage to chest. Deceleration, I think, is what that variable is. We have left leg and right leg impact measurements, and then a few other variables. DP, oh, you know what, I think all these variables are defined on the other page. DP is whether the dummy was a driver or a passenger. Protection indicates what type of protection there was, whether there was seat belts or airbags. Then we have whether it's a two or four door car, what year it was built in, what the weight is, and some indication of the size, whether it's like a medium size, a heavy, and so on, compact, I think. So let me go back to the previous page. Yes, there are all the variable names and their definitions. So pause the video and take a look if you want. So we're going to oh, I see, chest deceleration was all one variable. So we're going to end up looking at the head IC, head injury criterion, for these dummies as a measure of how much damage they got relative to whether it was a driver or a passenger, what sort of protection they had, I think how many doors they had, what year, what weight, and maybe another variable. So I'll bring it over to R again. So that's the story of the data. All this text is just stuff from that website. And I've put this data up on the course website. And let me just make this window a little bit bigger for now. So let me read the data set in and just print the names to the console. So we've got make, model, car ID, and I've already done a little bit of processing on this data so that it reads in well and it has variable names that are correct for R. Let's do a quick summary of these variables just to get a sense of what we're looking at. So the character variables, which most of them are, we don't really get a summary other than how many observations there are. But we have head injuries, which are either negative or positive. And the positive ones, I'll tell you that I coded those. When you look at the original data set, let me jump over there for a moment. There are some numbers with an asterisk. And I don't know what the asterisk means, but that was under the head injury criterion, this asterisk. If I go back to the previous page, there's no information about what the possible values are. So I don't know what that indicates. So what I did was I coded the data to, instead of a star, I coded it to be a negative number, and then I'm just going to take all the negatives and make them positive, because I don't know how to treat those minus signs effectively, because yeah, documentation's poor. Let's see what else we have. Chest deceleration, we're not going to end up using those variables. So basically what we've discovered is we need to start coding a bunch of these variables. Year, these are all 1900s cars, so 1987 up to 1991. We've got 5 years worth of vehicles. And then the weights of the cars, probably in pounds. All right, let's keep going. So here's I'm going to take the absolute value of the head injury criterion, make all those positive numbers. Oh yeah, there was some other coding issues. I ended up putting a minus sign. There were a bunch of how many doors a car has that were blank, and so I'm just going to code those as 4 doors, so we don't lose a bunch of observations due to missing this. And then I'll make the doors variable a factor variable. Oops. Let's see, D and P is whether you're a driver or passenger in the car. I'll make that a factor variable. So I'm going a little bit ahead here. Let's take a look at some of the data here. In particular, let's look at the head injury. Let's just plot a histogram of that. You see that this is quite right skewed. If I add a few more bins to the histogram, yeah, you can see sort of centered somewhere around 800 or so, and then we have this long right tail. So a lot of cars protect pretty well, and then there's some cars that protect very poorly. This car probably doesn't protect at all. So that right skewness may be an issue later on. Let's also look at, there's the car weight. Let's just type in WT for weight. Somewhat symmetric, but a few extreme observations. In fact, okay, so we'll look at weight. Initially, I was looking at how the head injuries and the leg damage scores related to each other, and thinking that maybe I would make a composite measure for how much damage the dummy received. But and even though there's some positive relationships here, it's not very strong. In fact, you can look at the correlation values; are very small down here. So we'll just look at the head injury score or criterion as the response variable. All right. So what I did is I create a variable called damage, and just assign the head injury criterion to damage. All right. So I'm going to subset the data to only include the few variables that we're going to do the analysis of. So we're going to look at how much damage the head of the dummy sustained, depending on whether you're driver or passenger, how much protection or what type of protection you have, how many doors are in the vehicle, what year it was made, and the weight of the vehicle. So I pressed Control Enter, it submitted it down here, and then the screen jumped because that's what it does. So now I'm going to create, I'm going to deal with protection. So there's a few values in the data set which are a bit unusual. If I look at a table of that protection, we see there's these 6 categories. D airbag is for the driver side airbag. D and P airbags means there's one on the driver side and one on the passenger side. Well, we have damage values for each individual dummy, and so really what we want as an indicator is if there was a driver side airbag in a car, this would indicate that there's one on the driver side but not one on the passenger side. So if there's someone in the passenger side of this car, they do not have an airbag. So we really want an indicator for whether they have an airbag or not. Everyone is going to have a seat belt, Now we've got manual belts, motorized belts, and passive belts, but I don't know that that really matters for a dummy. When these people are conducting these experiments, people are getting into the car, well, the dummies are, and people are putting the dummies into the car, and then they're strapping them in with the seat belt. So everyone has a seat belt on. You know, this really is about how humans behave, right? If you have a motorized belt, you're almost forced to have a seat belt come and restrain you as someone in this car, and so you can't drive without the seat belt effectively. Whereas a manual belt, you can just get in the seat and start driving, and maybe the car beeps at you, but you're not forced to wear that belt. Okay, so all this code right here is intended to deal with those issues. Do I have a belt or do I have an airbag? So first thing I do is let's see, DAT protection, I turn it into a factor variable, okay, and I make a table of it, same values as when it was a categorical variable. I'm going to create this new variable. It's a short version, prot, and I'm going to start off by assigning all the values NA. The first thing I'm going to do is if the protection type is in this list of some sort of seat belt, then I'm going to assign the DAT $prot the value belt. And I'm doing that because if they had an airbag, they would say airbag. So sort of lower class is belt, higher class is airbag. So I'm going to submit that line. Similarly, if you are a driver, okay, so if the DP, driver or passenger, indicates a driver and the protection is some sort of airbag, either driver airbag or DNP airbag, then that value is going to be an airbag. Similarly, if you're a passenger now, the only ones that relate to passenger are, for protection, is the D and P airbags. The P in there stands for passenger. So in those cases, we'll get an airbag. And and then I can make that a factor variable. You know, I realize that there's something here that's sort of missing. It could be the case that we've got a car that has a driver's side airbag, okay, but clearly that passenger would have a seat belt of some sort. So I think I really need to say in here, I need to create one more line, which is if you're a passenger and the protection is a driver airbag, singular, then that passenger gets a seat belt. Okay, I feel better about that now. So now if we look at a table, we've got 34 cars with seat belts, or 34 with airbags. Alright, and now I'm just going to delete the protection variable. One way to delete it is to assign null to it, and so it disappears from the data frame. Let's remove our missing values, look at the structure of the data frame. We've got 6 variables, with damage being the response variable. All the factor variables are coded appropriately, and damage DP, looks like all these variables are already correct. Alright, so we've got the data set we want. Let's make a scatter plot of these variables, and I'll make my plot window bigger before I run the plot code. There you are. And take a look at the relationships. So it looks like drivers are red, passengers are blue. That first column is damage. We see that it's right skewed for both drivers in red and passengers in blue. Obviously the number of doors is not going to depend on whether you're a passenger or driver. We have some scatter plots here for the weight of the car and how much damage. So it looks like there's a slight positive relationship here. The year of the car doesn't seem to matter very much in terms of how much damage, which isn't too much of a surprise. This is a 5-year window of that we're looking at. I realize I said 6 years before. This is 5 years. How much protection you have versus damage. Looks like there's, in this upper right-hand corner, the amount of damage you get if you have an airbag is way less than when you have a belt. Holy moly. All right. So let's start fitting our model. So the function fit. Okay, so this looked weird because the window was so small. So thanks to Erik, he had this idea of writing a function to do all the diagnostic plots all together, and so I went ahead and expanded on his idea. I wrote this function which takes the fitted value from linear model and it creates a ton of plots. So I'm just going to highlight this long function. There's the end of it, and submit that. So we've got that function now, and we're going to look at all the output of that function in a second. Let's start by fitting our full model. We're going to fit a linear model where damage is the response variable, and then I've got the other 5 variables on the right. I'm going to remove this log. And I've got this notation _2. So basically we're looking at the squared terms of all these. Though that's not exactly how the syntax is interpreted. So this square means that we get the main effects for each of the model terms, and we get the two-way interactions. Okay, so we get the main effects and two-way interactions. There's no quadratic terms, no higher order interactions. So let me fit this model, and we'll print out the ANCOVA table just to see what we've got for effects, and then we're going to look at the diagnostics. And then we're going to live in diagnostic land for a while. So here we fit the linear model. Here's our ANCOVA table, and we see we've got our 5 main effects, and then we have all the two-way interactions of that, as well as the line for residuals. And one thing to notice is that we don't have a lot of significant effects here, and that's largely because we have multicollinearity. We have a lot of variables that describe the same variability in the response, which inflates the variance for those effects, and we often won't see very much at this stage. We'll start to see how the effects are important as we reduce our model. All right, let's look at the model diagnostics for this model. And so I'm going to use my new function that I wrote, lm.diag.plots. I'm just going to put in the lm.full object and press enter. And in my plots window, I'll get a series of plots in different pages. So let me scroll back to, this is the last scatter plot. So we come forward 1, and we'll take a look at the residuals. One thing we see is we see some here's 0 way down here, and we see some right skewness. We see some influential observations, the leverage versus Cook's distance. There's a lot of high leverage points. I've added some lines here that we haven't seen before. These are rule of thumb style lines that I find to be helpful as a guide but not helpful as a rule. So this blue line indicates sort of points above which you should worry about how much influence they have on the fit of the model, and we have a lot of points above there, though I wouldn't use that as a hard rule about above and below. Similarly, I've got 2 vertical blue lines here about how large the leverage points are and whether we should worry about how much influence they may possibly have, and we see lots of points over those ranges. Let's take a look at the next. I've added a plot we've never seen before of collinearity, which actually doesn't tell us very much when there's interactions in the model in terms of in addition to main effects. Collinearity says how much variability is, well, actually, it's sort of just a measure of correlation between your predictor variables. And the reason that is a problem in a regression model is if weight and year are explaining similar amounts of information, say cars get bigger over time, so that there's a positive relationship between weight and year, then they both explain similar information, and so maybe you only need one or the other. So anyway, so we're not going to worry too much about this plot with the interactions in the model, because doors say, and interactions with door are going to be correlated because they both have doors in them. All right, QQ plots. Boy, look at that curvature. Definitely right skewed. Here's a new plot, Box-Cox power transformation. So we've never talked about this before. This transformation is a power transformation of the response variable. Basically, we have damage as a response variable over here on the left, and the question the Box-Cox transformation asks is, what exponent do I need to raise the response variable to in order to make our residuals the most normally distributed? Okay, so for example, we could raise damage to the second power, squaring damage. We could raise damage to a half power, taking the square root. We could raise damage to the -1 power. That would take the reciprocal of damage, 1 over damage. And so this x-axis down here in the bottom right, labeled lambda, indicates what power transformation we should consider. And we have a 95% confidence interval for that interval. And the special case is 0. If you raise damage to the 0 power, right, any number raised to the 0 power is the number 1. But the way Box-Cox is defined is 0 is defined as the log transformation. So right now, everything is pointing toward a log transformation. I'm going to look at the rest of the plots, and then I'll come back and summarize all that evidence. The next plots are about these residuals, and we see some right skewness on these box plots, though the difference in variability from one group to the other is not that great, except between airbag and belt. Okay, next plots. Again, here's 0 way down here, so we have some right skewness, but no real structure here in terms of slopes or curvature. Same thing here over years. So the main features here, let me page back up, is we've got a lot of right skewness. We have normality plots that shows the right skewness, and we have a suggestion that we should transform the response variable to the log scale. So that's a lot of information, all pointing toward log scale. So here's what you're going to do in your homework. You might find something like this. And so I'm going to scroll back up and find where I defined damage. Here's damage, and now I'm going to take the log of damage. All right, so let me take the log of damage and refit the model. There we go. And I'm going to clear my plots after each time, just so that I'm making sure that I'm not looking at the wrong plots. So we'll run that code. And we'll look at those residuals. Oops. And, oh, wow, here's 0, centered at 0. Let me make this plot a little bit bigger. These residuals look really good. There's a couple of outliers, but they're sort of in the middle of the data. Here's that line I was suggesting, and in my right now I would sort of ignore that. That rule of thumb I find not being terribly reliable. We have 2 observations up here which sort of are a bit outstanding, but the others don't look too bad. We have a lot of high leverage points, surprisingly. So continue to think about that for a little bit. Residuals look much more normal after having taken the log transformation, and now you can see the number 1 is at the center of the Box-Cox recommended power. So we've taken the log transformation, and we don't need to take any more transformation. We've we've fixed the normality problem, as you can see. More plots. Boy, those look pretty good in terms of equal variance over the driver-passenger, the number of doors, and the protection. And weight now is probably what's giving us this issue. So we have this sort of collection of points over here on the right, which are a bit outlying in terms of weight. Let's take a quick histogram of dat weight. And we see some right skewness here for dat weight. Let me add a few more bins here. Actually, it looks pretty symmetric except for a couple points out here. But I'm a little bit concerned about the, if we go back to the leverage point, how much influence some of these points have over here. And I'm willing to take an attempt to transform weight. Sorry for jumping around here. I'm just scrolling up to the top here looking for where weight is defined. And okay, I do have these two lines here where I take weight and I take the log of it, and then I remove the original weight variable. So I'm gonna basically start over because I've done a lot of. Actually, I think I can probably just do this. Let me just run this one line, and I will add the weight variable to the data set. And then when I fit my linear model, I just need to specify the new variable name, weight log, and I'll clear my plots, and I will run the model, and let's take a look at our residuals now. Oh, I'm using Control-Shift page up and page down because that's what this says. Oh, it says Control-Alt F12, but it turns out the Control-Shift page up and down also goes forward and back for the plots. So residuals look good. We still have quite a bit of leverage over here, but not that many points that are highly influential. I guess I'm not feeling too worried about that. Normality looks not too bad. Variances look okay, and taking the log didn't really help this very much. I think I would want to go back to my original scale for weight. Okay, so we explored a transformation with weight, and it didn't really help. So I'll just go back to what we had before. I'm going to rerun that. All right, so now the point is, it's looking pretty good in terms of residuals. So the next step is to do some model selection to try to find a more parsimonious explanation of the response. So I'm going to use BIC here. It's BIC because I'm specifying K, the penalty part of the information criterion, as being the log of the number of observations in the data set. Trace equals 1 means we'll get output after every variable that's either dropped or added. Notice I have direction both. It's going to start with the full model, so it's basically going to do backward selection, but both allows the rare situation of removing a bunch of variables but having a chance to reevaluate and add one of the variables that we originally removed. Because everything depends on everything else, that situation could happen. Alright, so I'm going to run model selection here. Let me clear my console window and then run the model selection, and we'll take a quick look at what was done. We arrive at a model that has AIC of a negative 1118 with this set of variables in the model. But we started way up here at the full model, and it started off considering whether we could drop any of the interactions, and we ended up dropping protection by year interaction, and then the next one was DP by protection, and so on. And so we just dropped a bunch of variables, and each time the AIC decreased by an important amount, so 1037, negative 1037, negative 1039, and so on. So I'm just going to scroll down until, so notice none is the line that says you have the best AIC when you don't do anything. When you add none or you remove none. So finally we remove doors and weight. Then doors, and we have a final model here, doors and a few interactions. All right. Get this window back. Let's final model. Okay. So I'm assigning the reduced model to the final model, and then we're going to look at the residuals for that final model. So we'll clear the plots out and look at those residuals. Alright, residuals look good versus fitted values. It looks like observation 5 may be worth a little bit of consideration here. Leverage points are not that high anymore. There's several beyond the second threshold, but most of them are quite small. Let me go to the next slide. There is a plot now that we hadn't seen before, but that only comes up when you've got a slightly smaller model, which is about homoscedasticity. So homoscedasticity is about the variability of the residuals. So along the vertical axis we have the absolute studentized residual. Basically it's the absolute value of the residual. Take all the negative values, make them positive. So 0 is way down here, and we notice that all the residuals are basically in the same spot, regardless of fitted value. There's a slight slope here, but this is not substantial in terms of relationship between the fitted value and the variance. So this looks really good. And that's something we could see over here too. On the original fitted values versus the residuals, the spread here is about the same regardless of what the fitted value is. Page back down. Here's collinearity. This is now worth looking at. Oh, you know what? This final model, we didn't. Let me tell you what terms are in this final model. I'm sorry. Here I've just printed out the ANCOVA table. Actually, here we just have the three main effects. DP, whether you're driver or passenger, has an effect. Prot is how much protection you get, and then the weight of the car. And all these are significant. There's no interactions, which is a blessing when you are an applied statistician hoping to interpret the results. You know, things aren't as interesting as they could be, but we can explain them with a fairly simple model, which is great. And then collinearity here, we've got weight, prot, and DP, and all these values are close to 1. 1 is wonderful. Okay, the variance inflation factor is how much. Let me do one more thing over here. Let me also print out the estimates in the parameter estimate table. Okay, using the summary. So what the variance inflation factor means is, so here's whether you're a passenger or driver, indicator variable. We have an estimate here for the amount of damage, and then we have a standard error. So if there was a correlation between, say, the driver and passenger and whether you had a seatbelt available or not, then they're explaining similar information. My example before was about the weight of the car and the year. Okay, if those variables are correlated, then the issue it creates is it takes the variance, or the standard error, of the estimates, and it inflates them. So by a certain multiple. And this horizontal axis is the multiple by which that variance is inflated due to collinearity or correlation between your predictor variables. An inflation of 1 is not an inflation. We start to worry when the inflation factor gets up around 10 or more. That sort of becomes correlation that's too strong for us. And at that point we want to maybe remove one of the variables or make a new variable which is a linear combination of the original variables, something like that. Alright, more residuals. Normality looks like we have a slight bit of kurtosis, but you know it actually doesn't look that bad. We are on the right transformation scale for the response variable. These box plots all look pretty good in terms of equivariance, and same thing there. There's no real structure with weight. So I'm feeling pretty happy with the model that we arrived at. All the residuals suggest the model fits pretty well. Normality is not too bad, which suggests that these p-values can be trusted in their interpretation. And we have a model with three main effects. And the resulting, so you know, the conclusions here would be that we now have to interpret what's going on here. Now we can't really interpret the intercept very well because the weight, that's for when passenger is 0, so the baseline for the DP is driver, the baseline for protection is the seat, is the airbag, alphabetically, and weight, if the car was 0 pounds, then this is how much damage you would get in that 35-mile-an-hour injury. I guess if your car weighed 0, that would be like running at the wall at 35 miles an hour, but we didn't test that condition. That's extrapolation. So we can't really interpret the intercept, but we can say that if we go from being a driver to a passenger, we actually expect less damage. There's a minus sign here if you're a passenger. If you wear a seat belt compared to an airbag, this is positive, so we actually expect more damage if you wear a seat belt. Basically, airbags help. And then weight is positive, which suggests that as you have a heavier car, you, as a crash test dummy, receive more damage. And that's the main thing I wanted to show you for this homework assignment. The main ideas here are that we kept going back to the residual plots. We at the beginning of the data portion of the code, we read our data in, and then we made some decisions. For example, we decided ultimately, actually we decided that we just use weight on the original scale. We decided to use damage on the log scale because the Box-Cox transformation and the residuals suggested to take the log transformation. And once we changed something, then we had to run everything again. But that's the beauty of using knitr, because then you can just click knit and it will run everything. So those are the main features of the homework assignment. Iteration. Start with a full data set, see what the residuals say, and use the evidence from the residuals to go back and make changes. And one thing I've added to the assignment that doesn't appear in this junky code here for this crash test dummy example is I want you to keep a little diary of decisions. Okay, and I have this written out in the assignment. I'll just bring that up real quick. Okay, so this is an unusual assignment because it's not top down, but you've got to go up, down, and up, down. And as you make decisions, you have to go back up to the top and try everything again. But keep a record of your decisions. For example, step 1, for the house and apartment listing prices, we're going to look at typical dwellings. And sorry, this is a little small. We're going to look at typical dwellings, the price for typical dwellings that are listed. And so the first step is to include only typical dwellings. So based on the scatter plot, we'll remove extreme observations, and you'll write code that keeps only those typical observations. Step 2, there's a few variables that have high correlation between them, and so we're going to remove a couple of predictor variables. Specifically, we're going to remove how many baths the apartment or house has and the size of the lot, because those are accounted for by basically how many bedrooms there are, and house size and lot size are somewhat similar. And so as you go through and jump up and down making all those decisions, keep this place in your notes for what decisions you made, why. Then, when you come back to this a year later, or when you have to give this to someone else for them to interpret, they can see what your logic was and how in all your decisions in a summary area without having to read all your code. There's also the second benefit that all your code is there so they can see what decisions you made, but this diary is going to help with the justification for why those decisions were made. And the why is just as important as what you actually did. Great, that was a longer video than I intended to make, but I think all those details are really going to help with this assignment. And have fun exploring the data and making decisions.